All right, today we're going to build a toolkit, but not for fixing your car. This is for understanding the entire universe. We're going to get into the language of physics, the fundamental rules that describe everything from a ball you toss in the air to how galaxies do their cosmic dance.
So where do we even begin with a task that big? You can't just look at the universe and guess how it works. No, we need a common language, a universal set of tools to measure things and make sense of it all. And that's exactly what we're going to put together right now.
Okay, first thing in our toolkit, a universal measuring tape and a stopwatch. Seriously. Before we can do any of the cool stuff, we all have to agree on the basics, like what a meter is, or a kilogram, or a second, so that a meter in one lab is the exact same as a meter on the other side of the world. And that global agreement, that's the SI system. You probably know it as the metric system. Think of it like the operating system for all of science. It's the common ground that makes every calculation, every single experiment, understandable to everyone, everywhere. And here's the really cool part. From just these three basic building blocks, the meter, the kilogram, and the second, we can construct almost any other unit we need. You want to talk about energy? The joule is just a clever combination of these three. It all comes back to these. But, the real world can be messy. What happens when you get a measurement in feet or miles per hour? Well, we just have to convert it. And here's the secret. You treat the units, like feet or hours, exactly like you would treat x in an algebra equation. It's a simple trick that lets you cancel them out. Let's try it with the Empire State Building. We know it's 1,472 feet tall. To get that into meters, we just multiply it by our conversion factor. And you see what happens? The feet unit on the top cancels out the feet on the bottom, which leaves us with our answer neatly in meters. It's a fantastic trick that works every single time. Okay, so we've got our units locked down. Now let's start describing the actual stuff in the universe. We're moving past just measuring things and into defining the real properties of matter. And this is where it starts to get really fun. And boom, just like that, by combining our units for mass and volume, we can define a core property of any material, density, right? Think about a block of styrofoam and a block of iron, both the exact same size. The iron is way heavier because there's just more stuff, more mass crammed into that same amount of space. That's density in a nutshell. So far, everything we've measured is about how much. But in physics, that's literally only half the story. To really understand things like motion or forces, we absolutely have to know which way. And that brings us to the next essential tool in our kit. Let me ask you this. If I told you I just walked 5 miles, could you find me? Absolutely no way, right? You're missing the single most critical piece of information. Which direction did I go? And this simple question gets at a huge idea in physics. That 5 miles is what we call a scalar. It's just a number. It's got a size, a magnitude, but that's it. No direction. Your age, the temperature outside, the price of your coffee, see? They're all scalars. They tell you how much, but they don't tell you which way. And this is where our powerful new tool comes in, the vector. A vector is the complete package. It has both magnitude and direction. It's not just 5 miles, it's 5 miles north. The best way to think about it is like an arrow. How long the arrow is tells you how much, and the direction it's pointing tells you which way. This chart just nails the difference. Look at your car's speedometer. It tells you your speed. That's a scalar. But your velocity? That's a vector. It's your speed plus the direction you're heading. See the pattern? A scalar gives you part of the story. A vector gives you the whole picture. Okay, so what happens when you're dealing with more than one vector at a time? Like maybe 2 people are pushing a box from different angles. You gotta add them together. But with vectors, it's not as easy as 2 plus 2 because, well, the directions matter. Visually, it's actually kind of easy. You just draw the vectors one after another, placing the tail of the next one at the tip of the last one. The grand total, what we call the resultant, is simply the arrow you draw from your starting point straight to your final endpoint. It's the ultimate shortcut. Now, drawing arrows is great for getting the idea, but for real precision, we need to use components. This just means we break every vector down into 2 simpler parts. How much it goes sideways, that's the x component, and how much it goes up or down, that's the y component. It's like giving each vector its own set of GPS coordinates. And this is where the magic happens. By breaking them down, you turn a tricky geometry problem into super simple addition. You just add up all the x parts, then you add up all the y parts. That's it. Those 2 sums are the components of your final answer. It's an incredibly powerful and simple technique. All right, for our final tool in the kit, let's talk about multiplying vectors. And this is where things get a little weird, honestly, because there isn't just one way to do it. There are two totally different ways to multiply vectors, and they give you completely different kinds of answers. This slide lays it out perfectly. First, you've got the dot product. It basically asks, how much are these two vectors aligned? And the answer it gives you is just a number, a scalar. Then you have the cross product. It asks a totally different question. What new direction is perpendicular to both of these? And its answer is a brand new vector. Think about it like this. If you're pushing a heavy box across the floor, the dot product tells you how much of your pushing force is actually helping to move the box forward. If you push straight down on the box, how much is it moving forward? 0. Your force and the motion are perpendicular, so the dot product is 0. Now the cross product has this really cool trick called the right-hand rule. Seriously, try it. Point the fingers of your right hand in the direction of the first vector. Then curl them toward the direction of the second vector. Whichever way your thumb is pointing, that's the direction of the new vector. This is absolutely essential for understanding anything that spins or rotates.
And there you have it. That's our foundational toolkit. With a standard set of units and the concepts of scalars and vectors, you now have the basic grammar and vocabulary to describe the physical world. You can literally speak the language of physics. So the only question left is, what are you going to go out and describe first?